Hi everybody, welcome to another video in linear algebra, section 4.3, linear independent sets and bases. Well, we already learned about linear independent. Right, let's review. An index set from V1 to Vp in vector space V is said to be linearly independent if the equation, this is a homogeneous equation by the way, has only trivial solution. Okay, linearly independent, only trivial solution. Of course, we have this way back in chapter 1, I believe, and we visit that almost every chapter. So linearly independent is where this equation only have trivial solutions. So we have linearly independent, this equation only trivial solution, meaning all of them are 0. And it is linearly dependent if it has a non-trivial solution, meaning one of them is not 0. In that case, it is called the linear dependent relation. Right. Theorem. If an index set V1 to Vp of two or more vectors with V1 not equal to 0 is linearly dependent if some vector is a linear combination of the previous vector. Right. Now, let's look at this example. Let's say P1 is a vector and P2 and P3, oh, that's a vector in the vector space of linear of the polynomial. So when we say vector space or a vector, it is not just a vector, it could be polynomial, could be a matrix, could be anything. When we go to the high level, we focus on pretty much the general concept. But at this level, usually the vector space is just mostly vectors. Sometimes polynomial could be matrix. Later on, could be a function, a little more complicated here. So he said, show that this set of these three vectors is linearly dependent. So this is linearly dependent, meaning that the solution, the homogeneous equation, has a non-trivial solution. But an easier way to say that, we can say P3 is equal to 4 minus t, or we can say P1 is equal to 1 and P2 is equal to t. So this is 4 times P1 minus P2. So since P3 is a linear combination of P1 and P2, this is linear dependent. It's a linear combination of P1 and P2. This is the set is linearly dependent. Right. Of course, if we move everything on one side, we have 4P1 minus P2 minus P3 equal to 0, and this has a solution, right? For C1 is 4, C2 is -1, and C3 is -1, and that is not a trivial solution, right? Originally, we have C1 P1, C2 P2, and C3 P3 equal to 0. Of course, we can see that C1 is 4, C2 is -1, and C3 is -1, and that is a non-trivial solution. If it has a non-trivial solution, it is linearly dependent. Right. Of course, like we said, if we can show one vector is a linear combination of the other vectors, they are linearly dependent. Right. Here's some example. The set of sine t and cosine t is linearly independent in the space of continuous function for t from 0 to 1. because sine t and cosine t are not multiple of the others. So if we only have two vectors, if one of them is not the multiple of the others, they are linearly independent. Determine if this set is linearly independent or not. Well, so here we need some trigonometry. Sine of 2t, double angle formula is what? 2 sine t cosine t, right? Here the sine t cosine t and the other sine t. So sine 2t is a multiple of sine t cosine t. So this set is linearly dependent because this is twice the others, right? So they are not linearly independent. So linearly dependent. Right? So if one is the linear combination of the others, or even better, one is the multiple of the others, it cannot be. Right. Next, sine square and cosine square, or sine square cosine square, we have the Pythagorean identity. Sine square plus cosine square equal to 1. So if we want to solve for sine t, sine square is equal to 1 minus cosine square t. And I can say is equal to 3 times 1 brought them backward. One over 3 times 3 plus negative 1 times cosine of t. Then cosine square of t. Then we say, why do we write in that way? Well, let's say this is v1 and this will be v2, this will be v3. So here we say this v1 is equal to 1/3 v3 minus plus negative 1 v2. So we say v1 is a linear combination of the others. So it is linearly dependent because one of them can be written as a linear combination of the rest. So linearly dependent. Right. So in differential equation we define what we call a Wronskian. A Wronskian is the determinant of just stack the function and then derivative, second derivative, and so on, and then we find the determinant. If it is not equal to 0 for all x in the interval, it is linearly independent. I'm just going to put that here. If later on we go back, we have time and go over the differential equation, then we revisit that. But for now, just going to leave it there. Right. Sorry, there's something wrong with the software. I have to restart the video. Basis. Let H be a subspace of a vector space V. An index set of vectors B1 to Bp in V is a basis if we have linearly independent, and second, it have to span the whole set V itself, meaning that I have a few vectors together and they are linearly independent, and if those vectors span the whole space H, then those will be the basis. With that definition, we have a basis of V is a linearly independent set that span V. So we have to have span and linearly independent. And it is equal because of any vector space is a subspace itself. The definition of basis implies that H equal to V. The case when that, because on the vector, because any vector space is the vector space is subspace to itself. That could be the case. And if it is not, then the requirement that each vectors must belong to H. Right. Now, let's go to this first example. The standard basis. E1 E2 to En is the column of the identity matrix. We already talked about this. So we said, for example, for R3, we have the vectors 1, 0, 0. This is E1, 0, 1, 0, E2, and 0, 0, 1. This set of these three vectors is a standard basis. Let's spell that correctly. Standard basis for R3. Right, so what does that mean? Now, I mentioned this a few times earlier. So we have the direction. Let's say if we want to travel on the plane two-dimensional space, we're going to need two directions. One to go forward, backward, and one is left and right. Those two directions together allow us to travel anywhere on the two-dimensional space or plane, right? So in that case, we call those two vectors form a basis for R2. Of course, it doesn't have to be perfectly orthogonal like this, perpendicular like this. It could be in any direction, as long as those two are different directions, meaning linearly independent. We can go anywhere on the plane by the combination of those two vectors. Now, if we want to travel anywhere in the space of R3, three-dimensional space, we're going to need three directions: one up, down, one forward, backward, and one left and right. With those combination of those three directions, we can go anywhere in the space, in three-dimensional space. So we say those three vectors form a basis for R3. Of course, it doesn't have to be perfectly perpendicular. It could be in some direction, but we're going to need three of them to go anywhere in the space. And furthermore, we cannot pick two of them in the same direction. So the vectors we choose to form the basis have to be linearly independent. Right. They have to be linearly independent. For example, on a plane of two vectors, we only have two vectors. This two will be good enough to be anywhere on the plane. Just the combination of those two directions allow us to go anywhere on R2. Having a third vector is redundant. We really don't need that, right? Because the third vector can be generated by the linear combination of the other two. And that is exactly what we have in this theorem. If we have from V1 to Vp are the set, and H is spanned by this vector, if one of them is the linear combination of the others, just throw it away. We can say that remove one of them out, is still span H. For example, if we have these two, only they span R2, having the third one is not necessary, so we just remove this. Two direction is enough to go anywhere on R2. Right. We see that in this example. Is the set of V1, V2, Vp linearly independent? Well, that's the reason we define linearly independent at the beginning of the section. Linearly independent is where the homogeneous equation has only trivial solution. Of course, we already have this. Right. Linearly independent, only trivial solution, meaning that no free variables. So we should not. So we should not have any free variable here. Right. So linearly independent equivalent to Ax equal to 0 has only trivial solution. And we put a question mark there. If it is, then it is linearly independent. So I just rewrite the question differently. Right, now we're just going to solve the homogeneous system. I'm going to set up the romantic matrix. And then just do the reduced row echelon form. Of course, we really don't need to enter the last column. It's going to be 0 regardless of the row operation that we apply to it. So I'm just going to say 3 by 3 here. Right, that's what we have. Right, we have a pivot here, and no pivot here. So because there's free variable, we have infinitely many solutions. That means the trivial solution is not the only solution. So because there's a free variable, so that means we have infinitely many solutions. That means we have more than trivial solution. So this is not linearly independent. Right, now if it's not linearly independent, can we write vector v3 as a linear combination of v1 and v2? Well, let's say in that case, that means can we write v1 times something and a2 times v2? Can we write like that? Well, I mean, certainly we can write like that, but is there an a1 and a2 that satisfy this equation? That's what I mean. So a1 v1 a2 v2 equal to v3. In the vector form, we will write v1 v2 together. Put v1 v2 into a column. And then we have a1 a2, yeah, and then v3. So in the first chapter, we have an exercise where we interchange between the vector form and the matrix form. That's why it comes in handy. Anyway, with that form, we can write that as romantic system, romantic matrix. Right, did we do that? Well, yeah. Sorry, the other way, that way. On the calculator, we already did that. Right. 0, 2, 6, 1. Yeah, so this gives us 1, 0, 5. Yeah, we just did that on the previous example, previous part of the example. So in this case, we have x1, x2, or in this case particular, a1, a2, and the pivot here and here. So obviously we have a1 is equal to 5 and a2 is equal to 3. So we say v3 is the linear combination of 5v1 plus 3 v2. Right, what we learned from the previous section is that if one of them is the linear combination of the others, just throw it away. So, and the question is, said what is the basis for H that span v1, v2, v3? In that case, we say the basis for H is, since v3 is a linear combination of the others, I'm just throw that away. We just need v1 and v2. By the way, because v1 and v2 are not multiple of the other, so v1 and v2 indeed are linearly independent. So it can be a basis, right? So the basis has two properties. It have to be linearly independent and it have to be span the whole space, right? So that certainly span because we write like that, but they are linearly independent. So that's why it is the basis, right? So to form the basis, if there anything that is make it linearly dependent, just throw them away. So we reduce the set until we have a set of linearly independent, and those set together we span the space that is that will form a basis for that space. Right. Now, from previous section is that when we get to this section, there's an easy way to find the vectors that represent the column space, the node space. Actually, the node space still the same, and the row space. Right here, what we have. The pivot columns of a matrix A form a basis for column A. Notice that we said this is the pivot column. If it is reduced to echelon form, that is obvious. However, when we choose the basis, choose the vectors for the basis, we're going to use the original pivot column and not in the reduced to echelon form. If two matrices A and B are row equivalent, then the row space are the same. That means if B is in the reduced row echelon form, the non-zero row of B form a basis for row space of A. Loosely speaking, basis for row space of A is the set of non-zero rows in reduced row echelon form of A. Not the case for the column. For the column, we have to look at the original matrix. Right. Here we have some example. Find the basis for row space, column space, and node space for this matrix. So first, let's find the reduced row echelon form of that matrix. I should choose the smaller matrix rather than the 4 by 5 here. But something like this make it less obvious. -2, -5, 8, 0. I didn't have 8. -17. 1, 3, -5, 1 and 5, 3, 11, -19, 7 and 1. One, 7, negative 13, 5, and negative 3. Right. So that is the reduced row echelon form, and obviously we have the pivot here, here, and here. So we just want to write the basis for the column space. The first one, basis for column space of A. It is very easy. We're just going to pick the pivot column, but not from here, but from here. We see the pivot will be the first column, second column, and the fourth column. So we're just going to list them. First column, second column, and third column. If I write that at fourth column, if I write that correctly. And the fourth column, sorry. Yeah. So that's simple enough. It's straightforward. Yeah. So reduce row echelon form, and then see where the pivots are. First, second, and fourth. Those are the columns that form the basis for column of A. Well, simple enough, right? Next, just write different row space, basis for row space of A. Basis for row space of A. That's simple. I'm just going to take the rows here in the reduced row echelon form. So that is the difference between the column space and the row space. So I'm going to write out the row. The non-zero row. Of course, if I have 0 in it, it's not going to be linearly independent. So that is the basis for the row space of A. Simple enough. Now the node space. Right. There's no other solution. We just look for solution of this. All the solution will be in the node space of A. So the node space is the set of all the solution to the homogeneous system. So I'm going to write, of course, I'm going to write the matrix A, and then 0, and then reduce row echelon form. Of course, we already did this. The 0 on the right hand side doesn't matter. It's going to be 0 on the right hand side. I just copy the reduced row echelon form from the previous one. That is the reduced rows echelon form for A, and 0 is still just a column of 0. Right, we have x1, x2, x3, 4, and 5. The pivot 1, 2, and those points. So the solution is x3 and x5 are free, x1, x2, and x4 will be in terms of those free variables. Right, so we say x1 plus x3 plus x5 equal to 0. I mean, from that equivalently I can write. From this we say x1 plus x3 plus x5 equal to 0, and then x2 minus x3 plus 3x5 is equal to 0, and then x4 minus x5 equal to 0, and of course 3 and 5 are free variable. Right, I put that together, we have the solution. x1 is negative x3 negative x5. Negative x3 negative x5. x2 will be x3 oh, I forgot the 2 here. Will be 2x3 minus 3x5. Right, negative x3 negative x5, 2x3 minus 3x5, and then x3 x4 is equal to x5, and x5 is 3. So when we write like that, we can generally split them in 2. Later on we will do this technique quite a few more times. Then we can factor out x3. Negative 1, 2, 1, 0, 0, and then x5 negative 1, negative 3, 1, 1. So we can say that the solution will be in this form, which is the linear combination of these two vectors, and obviously these two vectors are linearly independent, so they will form the basis. So I will say the null space basis for null space, null space of A are those two vectors, but usually if I run out of space when I cannot draw the column, I just going to write a row and then transpose it. That will turn it to a column. Yeah, so that is how we find the basis for the column space, the row space, and the node space for a matrix, right? Reduce row echelon form, pick out the columns for the column space, and the row space is in the reduced row echelon form. Column space we pick from the original, because if we're going to pick this, we're not going to have 0 on the last part of the vector, right? If we pick this, we're not going to have 0. We also always have 0 at the end. It's not going to work. So column space, pick from the original. Right, now we have this one. Good thing this is already in the reduced row echelon form, so we don't have to do much. So we already have reduced row echelon form. Right. So let's write for the column space of A. In this case, this is B. By the way, I just want to write this real quick. Even when we say those are the bases for column of A, that means we can say column of A will be equal to the span of those 3 vectors. Yeah. So that's what it means to be the basis. That means these vectors are linearly independent, and the vector will span the whole space that we need. And the same thing for the rest of the problem. Right. Now for column of B, the basis is the set of the vector. Because this is in the reduced row echelon form already, so we just have to keep the column. And the column space of B is a linear combination of these vectors, right? The row space of B, the basis are it's going to be in this form because it is already in reduced row echelon form, and so we're just going to write on the row that is non-zero. That's the row space of B, and now the node space. The node space is always the solution to the homogeneous system of equation. This is already in reduced row echelon form. Put in the romantic matrix, but it is already in reduced row echelon form, so we're just going to keep it. Don't have to do anything. Just going to write the equation that is the solution equivalent to this. Just this is period. So x2 and x4 are free. x1, x3, and x5 will depend on those x2 and x4 anyway. For x2 to x4, equal to 0, x3 minus x4 equal to 0, x5 equal to 0. Well, in this case we have x5 must be 0. 2 and 4 are free. Right. In this case, we will rewrite this as 1, 2, 3, 4, 5. Right, x1. Move this to the other side. x2 free, x3 equal to x4, x4 free, and x5 is 0. And then after we split, we should have x2 only have negative 4 and 1, 0 everywhere else. And then x4, we have negative 2, 0, 1, and 1. So we found the basis, this vectors and this vector. So that is the basis from no space of B. Right, more sample. For the basis for the column space, row space, and no space of A. That is A. So, of course, reduce row echelon form for that matrix. I enter the transpose version of it. 1, 4, 7, 2, 5, and 8, 3, 6, and 9. Right, that's what we have. Right, and from that we see we have the pivot here and here, so we can get the column space of A. The basis for column space will be the first and the second column, because that's where the pivots are. And then row space, the basis for row space will be this 2 row. And for the no space, we have to solve the equation, the homogeneous equation. Because when we do the reduced row echelon form, we're going to get that on the left hand side, and the right hand side is still 0. Which we can write as x1 minus x3 equal to 0, and then x2 plus 2x3 equal to 0. And in here we see that the pivots here and here. So x3 is the free variable, x1 and x2 we depends on it. So when we write the solution, x1 is equal to x3, x2 negative 2x3, and x3 is free. Factor out x3, 1, negative 2, and 1. So, in that case, the basis for the null space of A is equal to that. By the way, the null space of A is in this form. So we say the basis are the set of this vector. So the null space will be equal to the span of that vector. The row space will be the span of those two vectors, and the column space will be the span of those two vectors. Right. Now this example. The following three sets in R3 show how linearly independent set can be enlarged to a basis, and how further enlargement destroys linear independence of a set. Also, a spanning set can be shrunk to a basis, but further shrinking destroys the spanning properties. Right. So again, in this example, we're going to have R3. So we say, if there's R3 in the space of three-dimensional vector space, we're going to need 3 of them. Right. Actually, there will be a theorem in the later section about that. But we know that in R3 we're going to need 3 directions, so we're going to need 3 vectors in a basis. So 2 of them is not enough. That means we have to add 1 more to it. Now, we cannot just add any random vector into it. Original, by the way, those 2 are linearly independent. So that's good. At least we have something going here. Those 2 will generate a plane, for sure. But we're going to need 1 more to make into a space. Into a space of 3-dimensional space. So we're going to add 1 more, and we know for sure that this is not the linear combination of the other 2, because no way we have 0 here and 0 here that produce 6. So we know for sure the last one is not a linear combination of the other 2. Now we have 3 vectors that are linearly independent. That will be enough to show that this set is the basis for R3, because the span of these 3 vectors, I mean, if we have any 3 independent vectors, will span R3 and will be the basis for R3. Not the standard basis, but a basis for R3. Now, if we have too many of them, if we do the reduced row echelon form here, they guarantee to have a free variable, right? And if there is a free variable, that is not linearly independent. So because there will be a free variable here, so more than just a trivial solution. If we only have trivial solution, that is linearly independent. But if we have too many of them, too many vectors, they guarantee to have a free variable. therefore it's infinitely many solutions, meaning that the trivial solution is not unique. In that case, it's not linearly independent. However, when we have a bunch of vectors, it's guaranteed. If we have a bunch of vectors, like 4 different vectors here in R2, that different vectors, linearly independent or not, doesn't matter. That's guaranteed to span R2, right? We can check these 4 directions and we can go anywhere on a 2-dimensional space for sure. We don't need all of them. But if we have all of them, that's guaranteed to be span the whole space. Yeah, we can remove one of them, still spanning. But if we remove, that's still good. 2 of them is enough to span the whole space. But if we remove too much, one direction cannot travel the whole space. So in that case, here, if we have 2 vectors, it is not enough to span R3. We need one more. We need 3 vectors. At least 3 vectors to span R3. Actually, that is an incorrect statement. We need 3 independent right. So actually there will be a theorem later about this, but if we don't have enough vector, if we don't have enough current control, enough direction, we cannot travel the whole space. So we have to have enough, and when we have enough, those vectors still have to be linearly independent. In that case, that will be the basis. But having too many vectors, we lose the linear independent, because have too many of them, they guarantee to have a free variable. Right, we have a last example here. Let V1, V2 be that. Right, now, when we look at this, V1 is not a linear combination of V2. They are not multiple of the other row. So we say V1 and V2 are linearly independent. That's for sure. The set of this one is linearly independent. Because one of them is not the multiple of the other. Since we only have 2, that's all we care. They're not multiple of the other, so linearly independent. Now, determine if V1 and V2 can be a basis for R3. And this is basis for R3. The answer for that is no. Why is that? Remember, to span R3, we need to have 3 linearly independent vectors. So we do only have 2 here. It's not enough. Not enough vectors. We need 3 linearly independent vectors to be the basis for R3. Right, now, is that the basis for R2? That definitely not, because the vectors here in R3, so it cannot be a basis for another space, R2. So, since V1 and V2 in R3, it cannot be a basis. It cannot be R2, period. So we have 2 linearly independent vectors. not enough to be the basis for R3, and definitely not basis for R2. So what is the space where V1 and V2 are the basis of? Well, the answer for that is V1 and V2 are the basis of the space spanned by those two vectors. In that case, that could be a plane in three-dimensional space, but that guaranteed to be spanned by these two vectors, so we have the spanning properties, and that definitely linearly independent. We did say that before. So V1 and V2 will be the basis for this space. Right, so this section, of course, the most important is how do we find the basis for the column space, the row space, and the node space. And of course, we went over the definition of a basis. With that, we finished section 4.3. Thank you for watching, and see you in another video in linear algebra.